All right, so it's on to day 3 of Unit 6. We're looking at solving stoichiometry problems. If you want to follow along with the notes on page, got a couple examples to do here. In your packets, it should be page 8, day 3, stoichiometry. All right, let's take a look at the problems here. All right, so with problems in stoichiometry, there's only one new thing that we have to look at, and that's the molar ratio part of the process. So if you want to take a moment and fill in your notes here, you can start with quantity of given, and that's where you would have grams, volume, or particles, which is parts. And you probably recognize that from our work in the mole unit as a starting point for most of our problems. It was either in grams, volume, or particles, and you might be thinking already of formula mass and the 22.4 and the 6.02 times 10 to the 23rd, which are all ways that we would do those conversions. And that would allow us to convert to moles. So then we end up with the moles of given down at the bottom of the circle there, the U. You have moles of given. So here's the only new part of the stoichiometry unit is the use the molar ratio. In day 2 of this unit, we looked at how molar ratios work, and they're used to convert from moles of given to moles of unknown. So it's a conversion across the bottom there, where you use the molar ratio to figure out what you have for moles of unknown. Then the last step you have to do is convert to the desired units. So maybe you want grams, maybe you want volume, or particles or parts of unknown substance. So this will allow you to go through that last conversion using the formula mass, the 22.4, or the 6.02 times 10 to the 23rd. So that's the whole setup for all the problems. Each arrow represents a step in the conversion. So you can have up to 3 steps for stoichiometry conversion here in these examples. And so that's how that's set up. So let's do a problem. We'll do the hardest problem first. Let's say you have some Halloween candy kicking around still, which I hope you don't. But we want to figure out here how much you get out of a snack-sized Snickers bar. So it has around 10.5 grams of sugar in it, and we want to know how much water that's going to make. Okay, and this is for human body. And in the human body, if you eat a Snickers bar, obviously it's going to make urine, right? Moisture, liquid. And so the reaction for that is you have C6H12O6. And that's your sugar. Okay, then you breathe in oxygen, of course, I hope. And then that's going to make carbon dioxide. And you'll also make H2O. All right, so, in reality, most of the H2O is probably going to be expelled through respiration, so, breathing. But here we're going to just pretend that it all gets processed into the urinary tract, because that's funny, right? So what we have to do is balance this reaction, and we can see 6 carbons on this side. This is the biggest, meanest part of this whole thing. So I'm going to take the 6 carbons and try to get that to balance over here by putting a 6 there, and that's going to give me the 6 carbons I need, and it's also going to give me 12 oxygen. We'll take care of oxygen last. Then we have 12 hydrogens, so I'm going to come over here. I already have 2 hydrogens, so 6 times 2 will give me 12 of those. And I also get 6 more oxygens. So if you add those up, we have 12 and 6. Oh, wait a second. We have 6 over here already in the C6H12O6. So that takes care of these 6. We just need 12 out of this. So we're going to multiply this oxygen by 6. 6 times 2 gives us 12. And that will balance the equation. We need a balanced reaction in order to get it to get a ratio for the problem. Let's set it up. So remember, we're trying to figure out 10.5 grams of sugar, how many grams of water is that? So you always want to write down what you're starting with. We have 10.5 grams of C6H12O6, and we want to convert it to water. Now, if you remember in the diagram for the stoichiometry U that we just looked at, there are 3 distinct steps in order to convert. You have to convert to moles, you have to use the ratio, and then you have to convert to the desired units. So that's going to be 1, 2, 3 steps. And then we should be able to get grams of H2O in the end. Okay, so those are our 3 conversions: going to moles, converting to water, and going back to grams. Now the framework you're going to notice is the same for all these problems, where you have 1 mole on the top of the first step because you're converting to moles, and 1 mole on the bottom of the last step because you're converting to the desired units. All right, for us, this first step has to have the formula mass down here, you know, in order to convert it from grams to moles, which is, you know, what we're used to doing. And then in the last step, since we want grams of H2O, we're also going to need the formula mass here of water. Okay, so they're not the same formula mass because one is the formula mass of what you're given, the glucose, and the other is the formula mass of what you want, the water. Okay, in the middle we have our ratio. And the ratio, if you remember, is what the balanced reaction was all about. So let's set that up first because it's easier than finding the formula mass. So we'll do that here first. The ratio is always what you have on the bottom and what you want on top. Okay, we have C6H12O6 and we want H2O. Okay, now in the reaction, we see that in front of the H2O, there's a 6. So we're going to put the 6 here from that. That's where that goes. And then in front of the C6H12O6 over here, there's a 1. Okay, we'll put that 1 there. So it's a 6-to-1 ratio between the water and the glucose. So for every glucose molecule you ingest, it makes 6 water molecules. Okay. So that's the ratio step. That allows us to convert from glucose to water. All right, so I've been dancing around it. We got to find the formula mass here before we can move on. So looking at glucose here, it has 6 carbons. Carbon weighs 12 each. It's got 12 hydrogens. Hydrogens weigh 1 each. And it's got 6 oxygens. Oxygens are 16, it's 15.999, but so that gives us a formula mass of 180 grams. Now we also need the formula mass of water. Water has 2 hydrogens and 1 oxygen, so it's 2 times 1 and plus 16, so we have 18 grams. I like this problem because glucose is 180 and water is 18. I just think that's kind of funny that they're off by a factor of 10, you know, because I'm a nerd and stuff. All right, so doing the math, we're gonna take our calculator. Did I forget my calculator inside? Oh gosh, dang it. All right, so it's 10.5 divided by 180. 10.5 divided by 180, because it's on the bottom of the first step. Then multiplied by 6, because it's on the top of the middle step. And then multiplied by 18 to get our 6.3 grams. 6.3 grams of water. You should try to do that at home on your calculator. Make sure you get the same answer. Let's talk about the units. So the reason we set this up with the factor label method, that's what this is called, factor label method, is that it cancels out things across the conversion. Firstly, we get rid of grams here in the first step. We're dividing by formula mass in order to cancel grams out because we want moles, okay? Then we have our ratio step. This ratio actually cancels out the C6H12O6. That's what that's for. So C6H12O6 gets canceled out in the ratio step. Then we wanted our units to be grams and water. So we have to cancel moles out. So this last step cancels moles out from the first conversion. We cancel that out in the last conversion. So you can see that our answer will be water and it will be measured in grams. So it makes it very clear, you know, what process is going on and what's being canceled out as you're doing that conversion. Okay, so I consider those are the hardest problems because they involve a formula mass in two different places. And you know, that was kind of a complicated reaction to balance. So that adds a little bit of difficulty too. All right, let's go back and look at the next example. All right, how did we do? Balanced it right and got the right answer. Okay, good. All right, so I think this is pretty interesting. And as far as I know, this hasn't really been implemented yet in a vehicle, but Volvo was working on a passenger airbag system. Not passenger, pedestrian airbag system, because I guess this is quite a problem in Europe where they have a very, you know, population dense kind of area. There's a lot of people out standing in the middle of the road with their kid, I guess, I don't know. But there's a lot of fatalities involved in vehicular accidents. So some of the things they've done is tried to make bumpers not metal, you know, so it doesn't break people's legs. They've created hoods that kind of compact easier, and they have space between you and the engine. So, you know, the hood's not right up against the solid material. But one of the main problems is that when you're plowing through people on the road, you know, they're going to hit the windshield with their head. You get like a snap kind of whip reflex where they whiplash against the hard surfaces of the windshield. So how do we fix that? Well, we do it through a pedestrian airbag. Okay, so not a pedestrian airbag. So they have sensors that are developed in the front of the vehicle that can tell that you impacted, you know, something on the upper hood region, and that would deploy these airbags to cushion the blow. So you can see we have a bicyclist there who got hit by the vehicle and their head is nicely cradled against the windshield. And this adds to the airbag phenomena of vehicles where they already have, you know, 12 airbags, one in the windshield, one at your knees, one in the seat, one in the ceiling. Now they have them in the back seats too sometimes in some of the more expensive vehicles. Now we have airbags on the outside of the car. I like the picture at the bottom there that shows the entire car encapsulated with the airbag except for the grille. I feel like that's where we're going with these developments. But one of the funniest things was in the first test of this airbag system, they used a dummy, of course, and they, drove into it, hit it with the airbag. The timing was off, so the person actually hit the windshield, probably died, and then the airbag went off and launched the dummy off the road. So you could just continue driving, like, hey, no worries, no fuss, murder done, continue to travel, along the road with your visual area obstructed by a ginormous airbag pillow. So maybe we got to work out some of the kinks, but let's say you're working for Volvo and they have a job for you where they need you to develop a airbag system for their new car, okay? And what they tell you is that you have a pedestrian airbag that requires 64 liters of nitrogen. So to fill up across the windshield and cushion the blow of an impact, you need an airbag of 64-liter volume, and they need to know how much sodium azide you would need in order to do that. Okay, so this is the actual chemical that they use in airbags is NaN3. It's called sodium azide, is the commercial name. We would call it sodium nitrate if we were calling it by its chemical name, not its industrial name. So we need to figure out how many grams we need to put in there, so when you hit someone, if you hit someone, the airbag will fill to the correct volume. It won't overinflate and rupture. It won't underinflate and not do its job. It will fill up to the correct amount and cushion the blow of someone coming in contact with the hard surfaces of the windshield and framing of the vehicle, okay? So we need a volume of 64 liters, and we have our reaction there. Let's do the problem here together on the whiteboard. Okay, yeah, I think this is a great problem, except that I feel like airbags are kind of overused already because, you get in just a small fender bender nowadays, and it seems like you have to total the vehicle just because they're so expensive. So it was NaN3. I think it's got 3. Yeah. So interesting reaction because it's actually facilitated through an electrical impulse. There's sensors that can tell if you've struck something, and then it will fire off a spark, and that spark will, will set off the NaN3. That little spark is all it takes. So, all right, so we have 3 nitrogens over here, 2 over there. That's a common multiple of 6. So 3 times 2 is 6, and 2 times 3 is 6. That also gives us 2 sodiums. Okay, 2 sodiums, 2 sodiums, and that will be balanced. So there's our balanced chemical reaction, and we're going to use that for the ratio step in this problem. So let's write down what we have first. We're starting off with, we know we need an airbag that is going to produce 64 liters of nitrogen gas. Okay, that's what fills your airbag, is the nitrogen gas. Now, we're starting with liters this time over here for quantity of given. We have to still go through all 3 steps because we need to get to grams of the unknown. Okay, into the unknown. Into the unknown. All right, NaN3. That, hopefully you can see that. It's NaN3. I kind of ran out of room there. So again, same framework as last time. 1 mole on top of the first step, 1 mole on the bottom of the last step. We have ratio in the middle. So let's go ahead and set that up. 1 mole, 1 mole. Ratio. So ratio is N2 on the bottom because that's what we're starting with. And NaN3 on top. Now, in the balance reaction that we just balanced, we have a 3 in front of the N2 and a 2 in front of the NaN3. So it's a 2/3 ratio. So for 3 of these, you get 2 of those. It is important to notice here that you are ending up with more of the nitrogen gas, than the material that you start with. So that's good. It means it's going to blow it up nice and big. Now, this is in liters, you'll notice, meaning that our first conversion is our liters conversion, which we know we have a constant for, so that's great. We can just put the 22.4 in here for that. That's our constant conversion from liters to moles. Side note though, the airbags are really hot. If you've ever gotten in an accident before with airbags, luckily I never have. All my vehicles are too old to have airbags, but they come out really hot. So it's not going to be STP, as we say, like standard temperature and pressure. It's going to be high pressure because it's blowing up an airbag, and it's going to be really hot because it's an exothermic reaction. So if you tried to, for Volvo, do this calculation and use your STP conversion, you would get fired because you'd be killing pedestrians left and right. Your airbag would not function correctly. So you would have to figure out what temperature and pressure the airbag actually would be at and adjust this constant. But for us, we're just, some lowly honors chemistry students. We're going to stick with the 22.4 there. But, when you're working for Volvo, make sure you use the actual number. All right, now on this side of the conversion, we need to convert it to grams. So we do need to find the formula mass of sodium azide. So let's do that. All right, sodium is 22.98977. So we'll say that sodium is 23. And then it's got 3 nitrogens. Nitrogen is right there, 14. So we're going to do 3 times 14. And we'll add that up together. That's 65. Okay, so we have 65 grams for the formula mass for sodium azide, and we should be all set to run that conversion. So 64 divided by 22.4 times 2 divided by 3 times 65, okay? So you, anything that's not a 1, you have to multiply or divide by. The 22.4 is on the bottom, so you divide by that. 2 is on top, so you multiply by this. 3 is on the bottom, so you divide by that. And the 65 is on top, so you multiply by the 65, and you get 124 grams. So you need 124 grams of sodium azide. That would definitely make quite an explosion. I love how, and we're missing this because we're not at school, but auto collision every year they get an airbag out and they use a battery to jump it and pop it's like a steering wheel airbag, or sometimes they do the passenger airbag, and they'll put something on top of it, and it explodes, and it's really cool to see. So this is a lot of sodium azide. That'd be a really big explosion. So liters cancel out in the first step. That's why we have that set up there. Sodium cancels out, not sodium, sorry. Nitrogen gas cancels out in the ratio step, and then moles cancel out in the last step. So we have sodium azide and grams, which is what we want our answer to be, so that will work out correctly for us there, okay? So that's we'd call this one a mass to mass problem. We'd call this one a volume to mass problem. Let's look at one more problem and see if we can solve that one too. All right. Yeah, we did that one right. All right, so last problem, last example anyway, is how we can convert from liters to liters. So one of the reasons, I don't like cats too much is that their urine smells of ammonia. And I'm not sure why this is true. Maybe somebody that knows cats better than I do will know, but they have a high concentration of ammonia in their urine. And we all need this process because we end up with a lot of nitrogen dissolved in our blood and in our body, because most of what we breathe in and out is actually nitrogen, which doesn't really do anything for us. It's inert, and it kind of gets in the way. So what do we do with that? Well, we can combine it with hydrogen and expel it through ammonia, NH3. All right, so, oh, that's really stuck. I made my own special board cleaning solution though. And yes, it is flammable. Just in case I get attacked by another squirrel. I had one run right across the floor in here. Oh gosh. All right. There we go. So in this problem, you can see it. We have 15.5 liters of nitrogen. You would never have that much dissolved in your blood. That would be a real big problem. You'd have the bends for sure. So we have our reaction is N2 plus H2 gives you NH3. And we're starting out with 15.5 liters. Let me actually write that down here. 15.5 liters of N2. Okay, got that all written down. All right, so here we are. So we need to balance this reaction first. I know it was balanced already in the slide, but we'll just pretend we didn't see that. So we have 3 hydrogens and ammonia, and only 2 on this side. So you guessed it, we have to do the common multiple again of 6. So we're going to multiply this by 2. Oh, that might be perfect. 6, and then we can multiply this one by 3. Get 6. And we already had 2 nitrogens, so that's pretty awesome. So that's balanced. We can just put a 1 there just to kind of fill the void. So we have a 1, 3, 2 for balancing that. All right, now I'm going to do this in 2 ways. I'm going to do it the stupid way, and I'm going to do it the smart way. And you'll see why it's stupid here in a second. So let's say we wanted to set it up similar to the way we did it before, as you would with 3 steps. So you go first step, ratio step, last step, answer. We're looking for liters of hydrogen. It actually doesn't say, I guess. It's not a very good problem. It should say it wants liters of hydrogen. That's what we're looking for. So we're going from liters of nitrogen to liters of hydrogen. Can you see why this is a stupid way to set it up yet? All right, let's find out. So in the first step, we're going to have 1 mole and 1 mole, just like we did in our other one. And then for our ratio, we're starting with hydrogen. We want hydrogen, and we're starting with nitrogen. We just balanced this equation, so you can see it's a 3 to 1 conversion for the ratio. All right, and then because this is liters, we will need liters down here, and because this is liters, we need to convert to liters there. Are you seeing what the problem is here? All right, so we have 22.4 and 22.4 because we want liters for our answer, and we're starting with liters on this side. Here's the problem. The first step and the last step cancel out, right? Because it's the reciprocal of each other. We have 22.4 in the bottom, and we have 22.4 on the top. Those 2 steps actually would convert, would cancel one another out. So the only thing you really need is the middle, the ratio step, okay? You can do it this way. Like you can put it in a calculator, divide by 22.4, multiply by 3, multiply by 22.4, and you'll get the right answer, you know, because it will come out to the 46.5. But you can also simplify this quite a bit. Okay, so if you do take the 15.5, divide by 22.4, multiply by 3, multiply by the 22.4, you get 46.5 liters. Okay, but this whole thing could be much more, you know, easily set up if you cancel these steps out. Before, you know, we canceled individual units out, but in this problem, it actually cancels an entire step out. We still do cancel nitrogen out, okay, but really your answer is going to be hydrogen, and it's going to be liters, okay, which is what we wanted, liters of hydrogen. So what would happen if we rewrote this equation and instead just had the middle step? Right? Like if those steps actually do cancel out, you would actually get the same thing. Okay, so that's the better way of setting that problem up. You can set it up this way. It shows the whole process and it shows those two steps canceling out. Or if you come across a liters to liters problem, then you can just do the single middle step. And that's the quickest and best way to do that. Okay, so it's 15.5 times 3 gives you the 46.5 liters of hydrogen gas. Okay, so that's stoichiometry in a nutshell. Let me just leave you with one final thought here once I get this board erased. My special secret recipe works wicked good, doesn't it? It also works as a hand sanitizer. So I should like sell it on Amazon or something, huh? Board cleaner and hand sanitizer. And you know, if you're getting attacked, you can spray it in somebody's face and then get away. So there's a lot of benefits there. All right. So with stoichiometry problems, you're going to be given something in grams, you know, something in parts, something in liters, or maybe it's already given to you in moles, okay? So that will determine the first conversion, right? You're gonna have on top 1 mole, of course, but if you have that in grams, then the first step is going to need to have formula mass, right? That's the first thing you're gonna need. If it's parts, we didn't actually see any of these, but if it was parts, then you divide by the 6.02 times 10 to the 23rd, right? And then if it was liters, then you would divide by the 22.4, okay? But if it's moles, you get to skip that step because that step is to convert it to moles. So then you go to the ratio step. Okay, in the ratio step, you get numbers from the balanced chemical reaction. And this step is all about converting to what you want from what you have. Okay, so, or given, I guess I should say given, because That's what I wrote on this side is given. Okay, and so you need a balanced chemical reaction because you need to get these hashtags, you know, from these numbers from the balanced reaction. Those are the, you know, we'd call those coefficients from the balanced reaction. So that's how you convert from one thing to another. Your last step has 1 mole on the bottom. And then this is what you want over here. And you're going to want that in grams, parts, liters, or you may just need the answer in moles again, okay? So how do you set that up? Well, if you want grams for your answer, this is gonna be the formula mass, but it's the formula mass of what you want, not what you were given, okay? That's why it doesn't cancel out. Like mass to mass, the first and last steps don't cancel out because they're actually different formula masses. Now you might want parts, and then you'd use the 6.02 times 10 to the 23rd here to get parts. Which, if you started with parts and ended in parts, that would also cancel out. So you'd have only the ratio step if it was a parts to parts kind of conversion, okay? Just like the liters to liters. Liters to liters cancel out because in the first step you divide by the same thing that you multiply by in the last step. All right, so let's talk about moles because I haven't talked about the moles yet. Moles is a secret shortcut because if you start with moles, you actually get to skip and go right to the ratio step. And if your answer is in moles, you get to skip and go right to your answer. So moles to moles also is only the middle part of that conversion. Okay, so this diagram, I know you didn't really have a spot in your notes to put it, but maybe you can just stick it at the top where it says problem of the day or something and pause it here and write that in there. But the this will work with any of the stoichiometry problems you may come across. And it allows you to convert from any given quantity to anything you want in the units that you desire there. So again, these are all review because we use formula mass, we use the Avogadro's number and the 22.4 in the mole unit. The only thing new is the ratio part where you use the balance equation to convert from what you're given to what you want. So that's the real new thing. But these are, you know, kind of complicated conversions. So hopefully that helps you out. And if you have any questions or anything like that, please show up to the Zoom meeting so we can go over stoichiometry problems. Thanks.